Hello. Our project is scalable modeling and adaptive real-time trust-based communications. And I'm the PI for this project, Khan Iftekharuddin at Old Dominion University. My PIs are Jonathan Goodall, University of Virginia, Nasid Setin, Navid Tabildari, and Jean Chang, all from University of Virginia. And our community partners are Kyle Spencer from City of Norfolk, and RISE, a nonprofit organization here in City of Norfolk, Virginia. We have 4 tasks for this project. The task 1 is to generate real-time learning for street-level recurrent nuisance flooding RNF, the depth and extent of it. The second task is to create a new hydrodynamic real-time modeling. This is actually a physics-based model, and then transforming that to machine learning-based model. And then output from these 2 models will feed to the 2 tasks, task 3 and task 4. The task 3 will take these data and will create traffic flow models. And task 4 will take the data from all these and will communicate the risk factor to the drivers. The project vision, there are 2. We plan to develop the scalable modeling and adaptive real-time trust-based communication, and then evaluate the system for a flood-prone community here in Norfolk. There are 2 parts of this project: the user-inspired research part, which is actually inspired by the recurrent nuisance flooding here in Norfolk, and we plan to do automatic real-time detection of the extent and depth of the inundation levels and prediction of the RNF, and also the real-time communication of this information to drivers for them to plan ahead of time. The fundamental contributions, we are going to do real-time learning model for street-level flooding information. We'll also improve the community-scale road network flood prediction for RNF, and then improve the microscopic car following models for these flooded streets. And finally, we'll evaluate the effective risk communication strategies for the drivers. We made progress at least in 4 different areas. The first area is we are generating the synthetic urban recurrent flooding surf images, the videos. So this is a GAN-based surf generator. As you can see in this, in the 2 images that I'm going to play, on the left, there is this existing work on climate GAN, and on the right, using our surf generator, where we're actually using the city level flooding images, synthetic images, and videos. And the table below, the table 1, shows the accuracy of generating these video images for different objects here. Actually, the object is car in this case. On the right, we then worked on those video images, and we tried to enhance the quality, the texture and color of these video images using another layer of deep network in addition to the surf generator. So here we went through the process and then showed some result in table 2 for car and water segmentation using 677 flooding images and with different types of networks in table 2. And LinkNet gives us the best result out of these different types of networks for segmenting these cars and water, those 2 bodies or the objects in these synthetic videos. The goal is to take these videos and develop real-time learning for using the labeled images for water depth segmentation and depth analysis. The second area that we made some progress is this another way of flooding depth prediction using the height of the car, height of the car and the tire, both. And as you see on the left-hand side, left-hand panel of this slide, that we are able to implement this method, and the plot shows the mean absolute value error of water depth based on the wheel size of these 45 images. On the right, we are also taking a case study on usually on a street, Hampton Boulevard here in Norfolk, Virginia, where it floods frequently due to rain. And we're trying to obtain the 3D depth image using the 3D LiDAR. And this will also help us to do another type of depth computation for flooding. The third area that we made progress is dynamic modeling of coupled inland and coastal flooding. So here we are actually building a series of storm events and modeling for current and projected in the future, 2022, 2070, for different climate scenarios using this two-flow from Delta 3D model. So these are just preliminary data that shows that by 2070, tidal flooding will be dominant flooding mechanism with nuisance flooding expected to happen daily. On the right panel, this is just showing an integrated flow model, flow wave model for also developed in Delta 3D to simulate storm surge due to major hurricanes. And this is currently being calibrated. So the goal will be actually to bring all these models together to have the prediction capability in the RNF, water depth and extent analysis on the street levels. And the fourth area that we made progress in the communication part of the flooding information. Here we're trying to see the effects of flood warning types on perceived risk, trust, and actions taken by drivers in simulated driving situation. So we have participants that drove through these different conditions, the 4 different conditions that are shown on the left-hand side, from no flooding to some level of flooding. And then they are asked to decide on their decisions making, deciding whether they would like to drive through the street or they would do something differently. And the chart on the right hand side shows that for these drivers, the effect of flood information on percentage of participants displaying avoidant responses. And as you can see, that the trust was not affected by the flood warnings, although it was overall moderate. The evaluation of the project, we learned that roadside camera mounted to a major intersection in city of Norfolk cannot be achieved because the intersection, on the intersection, the poles are not owned by the city of Norfolk. So subsequently, we reached out to Dominion Power, the energy company, to access their electric distribution pole, but they could not help us either. So we came back to city. Now we are actually discussing with the city to mount some sort of solar operated camera on the traffic poles on the intersection. Anticipated outcomes and success measure. So we anticipate the collection of vehicle trajectory data on partially inundated roadways. We also are working on the simulated images like we discussed earlier. These are synthetic flooding images, realistic images. These will be used as label data to train the networks. We are looking at the effective flood risk communication through informed decision and social influence. And then this will be used for calibrating the trust. And of course, we'll like to publish journal papers. So this summarizes this whole project into 4 word charts, starting with the 4 tasks that we discussed earlier, and then going through the project vision, huge inspired research, and then finally fundamental research contributions. And we discussed all of these